Hello, Professor. My name is Mahir, and today I'll be presenting the final term project of EE267 called Swimmer Segmentation and Pose Estimation using SAM and YOLO V8. So, firstly, working with underwater footage introduces a unique set of challenges. First, underwater occlusions, things such as bubbles, splashes, and water distortions, these can obscure key joints or body parts, and these make the pose estimations unreliable. Secondly, the horizontal orientation of the swimmers is fundamentally different from most human pose datasets, which are trained on upright standing humans, and this in turn introduces a mismatch, and so it reduces the model accuracy unless we adapt the system. And lastly, dynamic motion is a big factor. Competitive swimmers move quickly and fluidly, which can cause motion blur and complicate the key point tracking from frame to frame. So our project is structured on four key objectives, and this can be shown here in a pyramid. At the base is a swimmer segmentation, which involves isolating the swimmer from the background. Next is the pose estimation, where we track body joint positions across frames, and this helps us analyze the technique and biomechanics under the water. Third, we have the use these pose features for stroke classification. So what it means is that the model learns to differentiate between four different strokes: freestyle, backstroke, breaststroke, as well as butterfly. And finally, at the top, we have model training and evaluation. And it is a continuous process of refining our models to work reliably across different swimmers as well as environments. Coming to the methodology, so what we will do is first we extract the frames from each video and sampling every 10th frame using OpenCV. Second, we isolate the swimmer using the SAM model with dynamic point prompts. And third, we use YOLO V8 for pose estimation, and we predict 17 body key points per frame. Then, based on these key points, we perform the stroke classification, and finally, we generate output visuals and JSON annotations, enabling both the visual analysis as well as the downstream data usage. Professor, as you can see here, the swimmer segmentation was a critical step to reduce the background noise as well as isolate the relevant motion. So, what we do is we start by converting the frames to grayscale, and we apply a threshold to highlight the brightest regions, and typically, which is the swimmer in the frame. Next, we find the largest contour to estimate the swimmer's position. We then feed this point into the SAM model, and finally, we filter the mass using size and shape constraints to remove the noise or irrelevant detections. And so, Professor, as you can see here, we have the before and after images, and this can show you how effective the segmentation was in eliminating the background clutter. After this comes the pose estimation. So initially I tried to use the YOLO V7, but it was having some PyTorch compatibility issues. So I had to proceed with the YOLO V8. And we use this model to detect the swimmer's joint key positions. So the model outputs 17 OCO format key points per person, and these cover major joints of the swimmer, such as the shoulders, elbows, hips, knees, and more. As you can see, all the 17 key points which are mentioned here. And finally, we apply the visual overlays there, and we draw colored circles on valid key points and connect them with the lines. So this helps us visually verify the pose estimation quality. And as you can see here, it's this is showing the pose estimation, and it's a confidence score of 86% for the person. After detecting the key points, we move on to stroke classification. Our approach here is entirely data-driven and does not rely on any hard-coded stroke labels. So first, we calculate joint angles, specifically between the elbow, hip, and knee. These were the 3 points that I took into consideration for each frame. And this gives us a compact representation of the swimmer's pose geometry. After this, what we do is we apply confidence filtering. So only joints with confidence scores above zero point 0.3 are used, and this ensures that we are working with reliable input. Then comes the pattern recognition. So each stroke, like freestyle or breaststroke, has distinct body positions and movement rhythms. So our classifier, what it does is it learns to recognize these patterns from the joint angles over time. Finally, the last step is the labeling of each frame as one of the four strokes, and the prediction with confidence directly onto the frame as a rectangular box, which I will show later in the presentation. So now I will show you the videos of all the four strokes. So firstly, this is the backstroke. And backstroke is the only strokes form on the back, and it is recognized by underwater arm pulls and consistent body roll, as shown here. So it's getting tracked in the swimmer's poses are getting tracked in a rectangular box, and it's also showing a confidence score. After this, we have the breaststroke. So in breaststroke, the symmetrical motion stands out. And this example shows the glide phase with the arms extended forward. And similarly here, as you can see, it's showing a confidence score and in a bounding box by Timer. So this is the breaststroke. And now we have the fly stroke. So the butterfly stroke is identified by simultaneous arm pulls and dolphin kicks, as you can see here, the swimmer is doing. So the system detects this frame with the confidence right at the peak of propulsion. As you can see here, it's also showing the confidence. Sometimes it's fluctuating to around 30%, and sometimes it goes up to 90%. So this is the butterfly stroke, and finally we have the freestyle stroke. So for freestyle, we just detect the alternating arm pulls and a streamlined board with a high elbow catch, as you can see the swimmer is doing. And also here, the confidence score, you can see it's fluctuating. It's sometimes it goes up to 85%, and then it comes down till 50%. So these were the video outputs that we obtained. So these are all the four strokes we saw earlier in the video. And now comes the confusion matrix. So the confusion matrix, it gives a clear summary of our stroke classification performance. And we evaluated our model across four stroke classes, and the rows show the ground truth labels and the columns show the predicted labels. So ideally, all the predictions should lie on the diagonal. And as you can see here, that's mostly the case. For instance, we had 84 backstroke samples correctly classified, with only one misclassified as a breaststroke and one as freestyle. And breaststroke had 97 correct classifications with a few errors spilling into adjacent classes. And I believe this is likely due to occlusion or similar limb positions between the different strokes. And also, butterfly is here. So, butterfly was recognized with a high accuracy. So, 107 correct predictions were made, and only a few were misclassified. And finally, freestyle also had a strong consistency. So, as you can see, 94 corrections were there. And overall, this matrix just shows that our classifier has learned distinct stroke patterns and is highly reliable. Now comes the classification performance. So on the right, you can see precision, recall, and F1 score for each of the four strokes. And all classes achieved F1 scores above 0.93. These were their max. And this indicates consistent as well as reliable classification. So from the graph, as you can see, the freestyle and the butterfly strokes delivered the highest scores across all the metrics. And this is because these two strokes tend to have a distinct and dynamic joint patterns, and this makes them easier to differentiate. Breaststroke, on the contrary, had slightly lower recall, and this is primarily because the breaststroke is basically a symmetrical motion. Limbs may become ambiguous in certain frames. And despite that, all the strokes show strong generalization, and these results confirm the robustness of our classifier across the board. After this comes the F1 confidence curve. So on the right, you can see the curve. We have the F1 score plotted again across the confidence thresholds for all the stroke classes. So the peak performance occurs at a threshold of 0.56, where the F1 score hits a 0.89. And what's important here is that all the strokes follow a similar trend. So performance increases with confidence initially, but then starts to degrade if we push the threshold too high. And the reason for this is overfiltering of valid predictions. So this analysis helps us fine-tune our threshold for balancing between the precision as well as a call. And we selected 0.56 as the operating point. So this gave us a good sample coverage. Here you can see the model training approach. So the model training approach was divided into five parts. Firstly, the videos that were given by you, Professor, I extracted like 1,000+ frames across all the four strokes, and these manually verified frames. So we had a rich data set, and also we did a pre-processing pipeline, so segmentation to reduce noise and frame selection of 300 to 400 best samples per stroke. After this, we also did a training strategy. So CNN classifiers were used for strokes trained on skeletons, and we also fine-tuned YOLO V8 pose with swimmer data. And speaking about hardware configurations, so Google Colab Pro was used with around 1 to 3 hour training cycles. And the matrix, as you can see here, as I earlier showed, accuracy as well as F1 score. we did. And talking about model training, so on the left, we have the accuracy graph showing both the training as well as the validation performance. And this gradually improves with validation accuracy stabilizing around 80%. And on the right is the loss curve. So the loss curve, both the training as well as the validation loss decreases steadily, as you can see. So this indicates that the model is learning well and not overfitting. So it both these graphs just confirm that our training strategy was successful. Lastly, speaking about the success rates, so these are the post-estimation success rates, and they just show how often the model could accurately detect the joint positions after the segmentation. So as you can see here, butterfly and the backstroke perform the best with over 89% success, and breaststroke and freestyle had slightly lower rates, likely due to the body curl as well as the occlusion. So as you can see here, we achieved a 91% accuracy for butterfly, 89% for backstroke, and around 77 to 78% each for breaststroke as well as freestyle. So to summarize our results, the system achieved strong accuracy across all the four swimming strokes, with classification F1 score peaking at 0.89. And we were particularly encouraged by the generalization of the model, despite the challenging underwater visuals and the swimmer variability. An important highlight is that the entire pipeline from segmentation to pose and stroke classification was learned end to end. We didn't rely on any hard-coded rules. And looking forward for future directions, we have identified three key areas for further improving the system. Firstly, the underwater specific fine tuning on both the segmentation as well as the pose models would help handle the bubbles, refraction, as well as the partial occlusions more effectively. Secondly, the current setup runs offline. So, extending this to real-time inference would open up new use cases and feedback as well as coaching. And finally, incorporating 3D post tracking could enable richer biomechanical analysis for performance monitoring or injury prevention. So overall, this project lays a strong foundation for swim analysis, and we believe the results show its potential for other real-world sports as well as research applications. Thank you.